The summer of 2018 was dry in Norway. Fields that were usually green turned yellow, then brown. Farmers worried about their crops. For archaeologists, the drought was an opportunity. The lack of water was stressing the vegetation, and stressed plants sometimes reveal what is hidden beneath the soil. At a farm in Jellestad, just south of Oslo, a farmer wanted to put in some new drainage ditches. He knew he had to get an archaeologist to check the land first. This area was known for its ancient burial mounds. The law required a survey, so archaeologists from the county of Ostfold came out to look. Their names were Lars Gustavsen and Eric Now. They didn't plan on digging. They had a better tool. It was a high-resolution georadar system, a kind of ground-penetrating radar. They mounted it on a small, all-terrain vehicle and started driving back and forth across the farmer's field. The radar sends signals into the ground. Those signals bounce back differently depending on what they hit. A rock, a ditch, or a piece of wood all create different echoes. They surveyed the field. The data appeared on a screen in their truck. At first, they saw what they expected: faint outlines of old farmhouses, some smaller burial mounds that had been plowed flat over the centuries. Then they saw something else. It was a clear, sharp anomaly. It was shaped like a boat, a very big boat. They stopped, they looked at the screen, the shape was perfect. It was a 20-meter-long Viking ship buried just 50 centimeters below the surface of the field. They could see the keel, they could see the individual strakes of the hull, they could even see the outline of the burial mound that once covered it. The plow had flattened the mound, but the ship was still there, a ghost in the radar data. They hadn't touched a shovel. They hadn't disturbed a single clod of earth, but they knew. They had found a Viking ship burial, one of the rarest and most important discoveries in modern Scandinavian archaeology. The technology had allowed them to see through the ground. It was a discovery made not with a trowel, but with radio waves. And it was just the beginning. The dry summer and a farmer's plan for a ditch led to a new window into the Viking Age. The technology simply showed them where to look. Number 15, we see things close erased centuries ago. Lars Gustafsson sat in his office in 2017 looking at maps. He was an archaeologist with the Norwegian Institute for Cultural Heritage Research, or NICU. He and his team were trying a new approach. For decades, archaeology meant finding a promising spot and digging. It was slow, it was expensive, and it was destructive. Once you dig a site, it's gone forever. You have only your notes and photos left. Lars wanted to change that. His team was pioneering the use of large-scale, high-resolution geophysics. It was a way to map huge, areas of landscape without digging at all. Their main tool was a ground-penetrating radar array. It wasn't a single unit. It was a whole rig of them, mounted on a cart that could be pulled by a small vehicle. This allowed them to cover entire fields, not just small test squares. They could survey a hectare in a few hours, not a few weeks. The Jellestad discovery in 2018 was the moment everyone noticed, but the work had started years before. The technology itself, LiDAR, or light detection and ranging, was the first step. LiDAR is often flown on a plane or a drone. It shoots out millions of laser pulses toward the ground. A sensor measures how long it takes for each pulse to bounce back. This creates an incredibly detailed 3D map of the surface. The real magic happens in the software. The computer can be programmed to filter out certain reflections. It can digitally remove all the trees. It can remove all the modern buildings. What's left is a naked map of the Earth itself. And on that map, you see things the human eye can't. You see the subtle lumps and bumps of burial mounds flattened by 1,000 years of farming. You see the faint lines of ancient roads and ditches. In 2016, a LiDAR survey of the area around Borre, another famous Viking site in Norway, revealed startling new things. Their archaeologists had studied Borre for over 150 years. They thought they knew it well. The LiDAR data showed them they didn't. The laser pulses, stripped of their tree cover, revealed the faint outlines of two massive halls. These were not ordinary longhouses. They were huge, probably feasting halls for a Viking king or chieftain. One was over 40 meters long. These buildings had been completely invisible, hidden under forest and farmland. This gave archaeologists like Lars the ability to direct their more intensive ground surveys. And they could use the bird's eye view from LiDAR to pinpoint exactly where to drive their ground penetrating radar. This is what happened at Jelstad. The LiDAR data showed a slight circular depression where a mound used to be. It was a good clue, but not definitive. It was the GPR that gave them the ship. The LiDAR showed them the right neighborhood. The GPR showed them the exact house. The process is changing how archaeologists think. They are no longer just excavators. Well, they are data analysts. They look at vast digital landscapes, searching for patterns. They can see how a Viking settlement was laid out in its entirety, not just one house at a time. They see the relationship between the burial mounds, the halls, the farms, and the harbor. The plows and the forests erased this landscape from our view centuries ago. LiDAR brought it back. It gives archaeologists a map of the past before they ever put a spade in the ground. Number 14, we found the ship's keel with radio waves. After the first stunning image of the Jelstad ship appeared on Lars Gustafsson's screen in 2018, the work was far from over. An anomaly on a GPR scan is one thing. Proof is another. The team needed more detail. They needed to be absolutely sure of what they were looking at. This is where the Ground Penetrating Radar, or GPR, went from a discovery tool to a surgical instrument. The system they used was developed by the Ludwig Boltzmann Institute for Archaeological Prospection and Virtual Archaeology in Austria. You know, it was a multi-channel array. Think of it like a lawnmower, but instead of blades, it has a series of radar antennas. The team, led by geophysicist Manuel Gabler, returned to the field. They set up a grid. They drove the GPR rig over the ship anomaly again and again, this time collecting data at an even higher resolution. They were gathering slices of data every few centimeters. The GPR works on a simple principle. It sends a pulse of radio energy into the ground. When that energy hits something different from the surrounding soil, something more dense or less dense or wetter part of the energy reflects back to the antenna. The machine records the time it took for the echo to return. This time translates into depth. By moving the antenna across the ground, you can build up a picture slice by slice of what lies beneath. What the team saw in the new Jelstad data was astonishing. It was better than a blurry ultrasound. It was a clear architectural drawing of a buried ship. The radio waves had detected the dense, compacted soil of the ditch that was dug to place the ship in the ground. This created a perfect outline. Inside that outline, they saw a strong, linear reflection running down the middle. It was the keel, the ship's backbone. It was about 18 meters long. Then, branching off the keel, they saw fainter lines. These were the reflections from the individual wooden planks, the strakes of the ship's hull. The wood itself was likely rotting away, but the process of decay had changed the soil chemistry and structure around it. The GPR was sensitive enough to pick up this subtle difference. They could count the strakes, they could see where the ship was widest, but there was more. The GPR also revealed other features inside the ship outline. It showed large circular shapes. These were the outlines of other burial mounds that had been built on the site before the ship was buried, and were then cut through by the ship grave. It also showed dark, disturbed areas inside the ship itself. These were potential burial chambers or pits for grave goods. The technology was not just showing them a ship, it was showing them a complex sequence of events, a history of the site written in soil and decay, read by radio waves. In 2019, they did a small targeted excavation based on the GPR data. They dug a narrow trench directly over where the GPR said the keel should be. They carefully removed the topsoil, and there it was. Not a reflection on a screen, but dark, rotted wood. It was the keel of a Viking ship. It was exactly where the radio waves said it would be, to within a few centimeters. The GPR had been their guide. It had allowed them to find the heart of the ship with minimal destruction to the rest of the site. It was a new way of doing archaeology, where the digging confirms what the data has already shown you. Number 13, A warrior's bones told us a different story. And for more than a century, the grave known as BJ 581 was famous. It was excavated in the 1870s by the archaeologist Hjalmar Stolpe in the Viking town of Birka in Sweden. It was the quintessential Viking warrior burial. The person inside was buried with a full set of weapons. There was a sword, an axe, a spear, 2 shields, and armor-piercing arrows. At the warrior's side were 2 horses, a mare and a stallion, buried with their master. For over 100 years, this grave was used as the textbook example of a high-status male Viking warrior. No one questioned it. Then, in the 2010s, a researcher named Anna Källström at Stockholm University was re-examining some of the bones from Birka. She was an osteologist and expert in skeletons. Looking at the bones from BJ 581, she noticed something odd. The pelvic bones seemed slender, the facial structure looked more typically female than male. She suggested that the famous warrior might have been a woman. Her suggestion was met with skepticism. Some argued the bones might have been mixed up with bones from another grave over the last 100 years. Others said that osteology wasn't definitive, the idea was controversial, the grave goods were so clearly those of a warrior, the assumption was that the person must be male. This is where a new technology provided a definitive answer. A team of researchers led by Charlotte Hayden Johnson at Uppsala University decided to test the bones using ancient DNA analysis, or ADNA. This technology was unimaginable in Hjalmar Stolpe's day. It allows scientists to extract and sequence the genetic code from centuries-old biological material. The process is incredibly delicate. DNA degrades over time. It can also be easily contaminated with modern DNA from the people handling the bones. The team took tiny samples from a tooth and an arm bone from the skeleton. They worked in a sterile clean room laboratory wearing full body suits to prevent contamination. They drilled into the bone to get to the powder inside, which was less likely to be contaminated. From this bone powder, they managed to extract fragments of the person's DNA. They then used powerful computers to piece these fragments together like a giant genetic jigsaw puzzle. The results were published in 2017. They were unambiguous. The analysis of the sex chromosome showed 2 X chromosomes and no Y chromosome. The warrior engraved BJ 581 was biologically female. The ADNA analysis did more than just confirm the sex. It also opened up new questions. The team analyzed the woman's mitochondrial DNA, which is passed down from mother to child. They compared it to the DNA of modern populations. Her genetic profile suggested she had connections to people who lived in what is now southern Sweden. The DNA gave her a history, a connection to a place. The discovery sent ripples through the world of Viking studies. It didn't prove that all Viking warriors were women. It proved that this one was. It forced everyone to re-examine their assumptions about gender roles in the Viking Age. The objects in the grave hadn't changed. The sword was still a sword, but the DNA changed the story of the person who held it. The bones, which had been in a museum drawer for decades, spoke a new truth, thanks to a technology that finally allowed us to listen. Number 12, an isotope signature revealed an army's journey. In the winter of 873 AD, a huge Viking force known as the Great Heathen Army made its winter camp at Repton in the heart of England. This was a turning point in their invasion. Repton had been a sacred site for the Anglo-Saxon kings of Mercia. By camping there, the Vikings were making a powerful statement. The Anglo-Saxon chronicles tell us they were there. For years, archaeologists looked for evidence. In the 1970s and 1980s, archaeologists Martin Biddle and Bertholby Biddle excavated at Repton. They found the camp's defensive ditch. They also found a burial mound. Inside, they discovered the jumbled bones of at least 264 people. About 80% of the skeletons were male, most of them of fighting age. Many showed signs of violent death. It looked like the burial site for the Viking army, but there was a problem. Radiocarbon dating of the bones at the time gave a wide range of dates. Some bones seemed to date to the 7th and 8th centuries, long before the Great Heathen Army arrived. Others seemed later. The jumble of dates made it hard to say for sure that this was the army's mass grave. For decades, the Repton grave remained a puzzle. In the 2010s, a new team led by archaeologist Kat Jarman decided to look at the bones again, this time with new technologies. One of the most powerful of these was strontium isotope analysis. Strontium is an element found in rocks and soil. It enters the food chain through water and plants. As we grow, strontium from the food we eat gets incorporated into our teeth and bones. Different geological regions have different, unique strontium isotope ratios, like a geological fingerprint. Your tooth enamel forms in childhood and doesn't change, so the strontium signature in your teeth is a permanent record of where you grew up. Your bones, however, are constantly remodeling, and their strontium signature reflects where you've lived in the last 7 to 10 years of your life. And Kat Jarman and her team took tiny samples from the teeth of several individuals in the Repton mass grave. They used a mass spectrometer to measure the strontium isotope ratios. The results, published in 2018, were transformative. The strontium signatures showed that these people were not from Repton. They were not from England at all. Many of the individuals had strontium ratios consistent with the geology of Scandinavia. One individual had a signature that pointed directly to southern Norway. Another matched the profile for southern Sweden. They were immigrants. This was powerful evidence that the bodies belonged to the Viking invaders. But there was an even bigger surprise. The strontium analysis also revealed something about the makeup of the army. It wasn't just men from one part of Scandinavia. The isotope signatures were varied. They came from different parts of the Viking world. This supported the idea that the Great Heathen Army was not a single unified force, but a coalition of different warbands from across the north. Combined with new, more precise radiocarbon dating that confirmed the bones did indeed date to the late 9th century, the strontium analysis solved the Repton puzzle. It proved the mass grave belonged to the Great Heathen Army. More than that, it gave a voice to the individuals within it. It told the story of their origins. It turned a pile of anonymous bones into a map of a migration, a chemical record of a journey from a childhood home in Scandinavia to a warrior's grave in the middle of England. Number 11, we searched for Vikings from space and found a lesson. In 2015, the world of Viking archaeology was buzzing with excitement. A press conference announced a potential breakthrough. A new Viking site may have been found in North America. This would be only the second confirmed Norse site on the continent after the famous Lance Aus Meadows in Newfoundland, discovered in the 1960s. The new potential site was 500 kilometers south, at a place called Point Rosy, and it was found not by someone stumbling across it, but by a scientist looking at pictures taken from 600 kilometers up in space. The scientist was Dr. Sarah Parcak, a pioneer in the field of space archaeology. She used satellite imagery to find lost sites. Her technique involved analyzing images in the infrared spectrum. Healthy vegetation reflects infrared light very strongly. But if plants are growing over, the buried remains of a wall or a building, their roots can't grow as deep. They get less moisture, they become stressed. This stress, often invisible to the naked eye, shows up clearly in infrared satellite images. The plants look slightly different. Dr. Parcak had used this technique to find thousands of lost sites in Egypt. She wondered if it could work for finding Norse sites in North America. The challenge was different. Instead of stone ruins in a desert, she was looking for turf walls in a grassy, boggy landscape. She scanned satellite images of the coast of Newfoundland. At Point Rosy, she saw something. There were faint, rectilinear shapes in the vegetation, a dark stain in the soil that looked like it could be a hearth. It was a promising anomaly. In 2016, a team including Parcak went to Point Rosy to investigate. It was a major international effort filmed for a television documentary. They began to dig. The initial results seemed to confirm the satellite data. They found a turf wall. They found a feature that looked like a hearth used for working iron. They found ash and chunks of roasted bog iron ore. This was exciting because ironworking was a key Norse technology. Native peoples in Newfoundland at that time did not work iron. The team collected samples of the material from the hearth and sent them for radiocarbon dating. The world waited. The initial discovery was hailed as a triumph of modern technology, a Viking site found from space, but science is a slow and careful process. The full results of the excavations and analysis were published in 2017. The news was not what everyone had hoped for. The radiocarbon dates came back and they were not from the Viking Age. The turf wall turned out to be the result of natural processes. The hearth was likely the remains of a more recent local attempt at ironworking, or perhaps even a lightning strike that had superheated the bog iron. It was not a Norse settlement. The Point Rosie story is important, not because it was a failure, but because it shows how science really works. The technology did its job perfectly. The satellite imagery identified a genuine anomaly on the ground that was worth investigating. It got the archaeologists to the right spot. But the technology is only a tool. It generates questions and possibilities. The answers still have to come from careful, methodical work on the ground, from digging and dating and analysis. Dr. Parkak was honest about the results. It was a lesson in the scientific method. You form a hypothesis. You test it. Sometimes the test proves you wrong, and that's not a failure, that's just learning. The search for Vikings from space didn't find a new settlement, but it did show the power of the tool and the importance of scientific rigor. Number 10, we are saving a shrinking ship with lasers and light. The Oseberg ship is a masterpiece excavated in 1904 from a burial mound in Norway. It is the best preserved Viking ship ever found. So it is over 21 meters long, built of oak, and covered in intricate carvings of animals and patterns. It was buried in 834 AD as the final resting place for two powerful women. For over a century, it has been the star attraction at the Viking Ship Museum in Oslo, but the Oseberg ship is in trouble. It is falling apart. The problem dates back to its original conservation. When the ship was excavated, its waterlogged wood was treated with alum, a chemical salt, to stop it from shrinking and cracking as it dried. This was the best method they had in the early 20th century, but it was a terrible mistake. Over the decades, the alum has reacted with the wood, breaking it down from the inside. The wood is becoming acidic and brittle. Some pieces have shrunk by as much as 15%. The masterpiece is slowly destroying itself. For years, conservators at the Museum of Cultural History in Oslo have been fighting a desperate battle to save the ship. They need to develop a new way to preserve the wood. But before they can test new treatments, they need a perfect record of the ship, as it is now. They need to capture every curve, every tool mark, every crack, every millimeter of its complex shape. Actually, they need a digital twin. Starting in 2013, a major project began to create an ultra-high-resolution 3D model of the Oseberg ship. The technology they used is a combination of laser scanning and photogrammetry. A laser scanner sweeps a beam of laser light over the surface of the ship. It measures millions of points, creating a point cloud that maps the ship's geometry with sub-millimeter accuracy. This photogrammetry works differently. A photographer takes thousands of high-resolution, overlapping digital photos of the ship from every conceivable angle. Specialized software then analyzes these photos. It identifies common points in multiple images and uses them to calculate the object's 3D shape and texture. The result is a photorealistic model. By combining the geometric precision of the laser scan with the realistic color and texture from the photogrammetry, the team is creating the most detailed digital replica of a historical object ever made. It is a massive undertaking. Just the ship's prow with its complex animal carvings required thousands of photos and scans. This digital Oseberg ship has several crucial purposes. First, it is a tool for conservation. The scientists can use the 3D model to track changes in the wood over time. They can measure shrinkage and decay with incredible precision. They can run simulations to see how the ship's structure is being stressed. Second, it is a tool for research. Scholars from around the world can now study the ship in minute detail on their computers without ever having to travel to Oslo. They can zoom in on a single tool mark left by a Viking shipwright 1,200 years ago. They can analyze the carving styles in ways that are impossible with the naked eye. Finally, it is a form of preservation itself. If the worst should happen and the original ship cannot be saved, its digital ghost will survive. The model is so detailed that it could be used to 3D print a perfect replica. The technology is creating a life raft for a priceless piece of history. It can't reverse the damage done a century ago, but it can ensure that the Oseberg ship, in one form or another, will not be lost to future generations. Number 9, we mapped the first farms to understand a nation's birth. The settlement of Iceland, the Landnam, is one of the great stories of the Viking Age. Starting in the late 9th century, Norse settlers crossed the treacherous North Atlantic to a new, uninhabited land. The Icelandic sagas tell us who these first settlers were, but they don't tell us how they did it. How did they choose where to build their farms? How did they organize the landscape? How did a society form from scratch in this new, harsh environment? For years, archaeologists have been excavating early Viking Age farmsteads in Iceland. They have found the remains of longhouses, animal pens, and workshops, but each excavation only gives a snapshot of one farm. It's hard to see the big picture. How did this farm relate to its neighbors? Where did they graze their sheep? Where did they get their wood? Dr. Douglas Bollender, an archaeologist at the University of Massachusetts, Boston, has spent years working to answer these questions. His most powerful tool is not a trowel, but a computer program, a geographic information system, or GIS. GIS is essentially a smart map. It's a system for capturing, storing, analyzing, and displaying all types of geographical data. An archaeologist can use GIS to create a map of a region and then layer different kinds of information on top of it. You can add a layer for elevation, a layer for rivers and lakes, a layer for soil types, a layer for vegetation. Into this digital landscape, Dr. Bollender and his team began to add archaeological data. They mapped the locations of all the known Viking Age sites in a specific region of northern Iceland, the Skagafjordur Valley. They added the locations of longhouses, burial sites, and other structures found through excavation and survey. With all this data in one place, the GIS becomes an analytical engine. The researchers could start asking complex questions. Was there a pattern to where the first settlers built their homes? The GIS could analyze the location of every early longhouse against the data layers for elevation, slope, and proximity to fresh water. A clear pattern emerged. The earliest farms were almost always built on low-lying, south-facing slopes near a reliable water source on the best patches of soil. The settlers knew exactly what they were looking for. The GIS also helped them understand how the landscape was used. Or they could map the infield, the fertilized land, close to the farmhouse used for growing hay. They could then model the outfield, the vast areas of common pasture where sheep and cattle would have grazed. By analyzing the size of the longhouses and the likely number of animals they could support, the GIS could calculate how much grazing land each farm would have needed. This led to a major insight. The model showed that the best land in the valley was settled very quickly, within a generation or two. As new settlers arrived, they had to move further up the valley into less ideal areas. The GIS allowed the team to see the process of settlement unfold across the landscape over time. It showed how the first arrivals claimed the prime realities and how a social hierarchy might have begun to form based on the quality of one's land. The technology didn't dig up any new artifacts, but it took all the data from decades of hard physical archaeology and put it into a context. It connected the dots between individual farms, it revealed the logic of the landnam, it created a dynamic map of a society being born, one farmstead at a time. Number 8, a handheld scanner unlocked the secret of a legendary sword. There is a group of Viking Age swords so famous they have their own name, Ulfbert. About 170 of these swords have been found across Europe, from Ireland to Russia. They are all marked with the inscription Flufbear Plust. They were the high-tech weapons of their day, made of a steel so pure and strong that it baffled modern blacksmiths. European smiths at the time were making swords by forge, welding different strips of iron and steel together. It was a good technique, but it left impurities in the metal. The Ulfbert swords were different. They were made of crucible steel, and crucible steel is made by melting iron with carbon in a sealed clay pot, a crucible, at very high temperatures. This process removes impurities and creates a homogeneous high-carbon steel. The result is a blade that is incredibly strong, flexible, and sharp. The problem was this technology was not thought to exist in 9th century Europe. It was a technique perfected in Central Asia and the Middle East. So how did a Viking Age smith in, say, the Rhineland get this material? For a long time, the only way to analyze the metal of a sword was to cut a piece off. This is something museums are very reluctant to do to a priceless 1,100-year-old artifact. The mystery of the Ulfbert swords remained locked inside the metal. Then, in the 2010s, Dr. Robert Lehmann, a materials scientist from the University of Hanover, began a new study. He had a tool that could see inside the swords without leaving a mark. It was a portable X-ray fluorescence, or XRF, analyzer. An XRF analyzer is a handheld device that looks a bit like a price scanner at a supermarket. You hold it up to an object, and it shoots out a beam of X-rays. These, the 10th rays, knock electrons out of their orbits in the atoms of the material. As other electrons fall into the empty spaces, they release a secondary burst of X-rays. The energy of these secondary X-rays is a unique fingerprint for each chemical element. The XRF device reads these fingerprints and tells you exactly what the object is made of. It is completely non-destructive. Dr. Lehmann traveled to museums across Germany and Scandinavia. He was allowed to take the priceless Ulfbert swords out of their cases. He simply held the XRF scanner against the blade and pulled the trigger. Within seconds, a detailed chemical analysis of the steel appeared on the device's small screen. The results were stunning. The XRF data confirmed that the true Ulfbert swords were made of crucible steel with a high carbon content and very few impurities, or slag. But it also revealed fakes. Some swords had the Ulfbert inscription, but were made of the lower quality pattern welded steel. It seems that even in the Viking Age, brand piracy was a problem. The name Ulfbert was so famous that lesser smiths were stamping it onto their own inferior blades. The XRF analysis also provided clues to the steel's origin. The chemical composition, including trace elements, did not match any known European iron sources from the period. It did, however, match the profile of crucible steel produced in what is now Uzbekistan and Afghanistan. The handheld scanner had revealed a vast trading network that stretched from the heart of the Islamic world, up the rivers of Russia, and into the hands of a Viking Age swordsmith. The technology showed that the Viking world was not isolated. It was connected by long-distance trade routes that moved not just silk and silver, but the most advanced materials science of the era. The secret of the legendary sword was not just a recipe for steel, but a story of global connection. Number 7. We dated a ship's timbers to the exact year and forest. In 1962, a major discovery was made at the bottom of Roskilde Fjord in Denmark. Archaeologists found the remains of 5 Viking ships. They had been deliberately sunk around the year 1070 to block the main channel into the city of Roskilde, protecting it from seaborne attack. The ships were carefully excavated from the seabed piece by piece. They became known as the Skuldelev ships. The ships were a treasure trove of information. They were different types. There was a long, slender warship, a deep, broad cargo vessel, a fishing boat. They represented a cross-section of Viking maritime life. But one big question remained. Where did they come from? Were they built locally in Denmark, or did they come from further afield? The answer came from the wood itself and a technology called dendrochronology, or tree ring dating. You know, every year a tree adds a new growth ring. The width of that ring depends on the growing conditions of that year. A warm, wet year produces a wide ring. A cold, dry year produces a narrow one. Over the life of a tree, this creates a unique pattern of wide and narrow rings, like a barcode. Scientists can take a core sample from a living tree and map its ring pattern. They can do the same for old wooden beams from historic buildings. By overlapping these patterns, they can build a master chronology for a specific region that goes back hundreds or even thousands of years. In the 1980s, dendrochronologist Niels Bonde at the National Museum of Denmark began to study the timbers from the Skuldeleve ships. He took thin slices of the oak planks and beams. He carefully measured the width of each ring under a microscope. He then plotted these patterns on a graph. He started with Skuldeleve 3, a small cargo ship. He managed to create a 136-year-long ring pattern from its timbers. He compared this pattern to the master chronology for Denmark. It didn't match. He tried the chronology for southern Sweden. No match. He tried Norway. No match. Then he compared it to the chronology for the area around Dublin, Ireland. It was a perfect match. The analysis showed that the tree used to build the ship was felled in the year 1042 in the woods outside of Viking Dublin. A Danish ship, it turned out, was Irish built. This was a huge discovery. But the biggest surprise came from Skuldeleve 2, the great warship. This ship was over 30 meters long, a true ocean-going raider. It was assumed to be the pride of the Danish fleet. Niels Bonde analyzed its timbers. He found the same thing. The ring patterns matched Dublin. The great Danish warship was also built in Ireland around the same time, 1042. Dendrochronology did more than just date the ships. It rewrote a chapter of Viking history. It showed that the Viking world was incredibly interconnected. A king or chieftain in Roskilde, Denmark, had the power and resources to commission a state-of-the-art warship to be built in his territories in Ireland, and then have it sailed back to Denmark. The technology turned the ships from anonymous artifacts into specific historical documents. It pinpointed their date of construction to a single year. It pinpointed their place of origin to a specific forest. It told a story of power, resources, and a maritime network that spanned the northern world. All of this was read from the silent, unique language of the trees. Number 6. We read the story of a lost colony in ancient Poland. For nearly 500 years, from the late 10th century to the 15th century, the Norse had a foothold in Greenland. They established two main settlements, the eastern and the western settlement. They built farms, raised livestock, and erected churches. Then they vanished. The disappearance of the Greenland Norse has been one of history's great mysteries. Was it a sudden catastrophe? Were they wiped out by disease or in conflict with the local Inuit? Or did they just pack up and leave? The answer, it turns out, was preserved in the mud at the bottom of Greenland's lakes. And the key to reading it was the science of palynology, the study of pollen grains. Every year, plants release vast quantities of pollen. These tiny grains are incredibly tough. They can be preserved for thousands of years in sediment layers like those found at the bottom of a lake. Each plant species has a unique pollen shape. By taking a core sample of the lake sediment and analyzing the pollen in each layer, scientists can reconstruct what the landscape and vegetation looked like at different points in time. The deeper you go in the core, the further back in time you travel. Starting in the 1990s and continuing to this day, researchers like Dr. Jette Arneborg from the National Museum of Denmark have been using pollen analysis to investigate the Norse settlements. They took sediment cores from lakes near the old farm sites. In the laboratory, they would take tiny samples from the core at regular intervals. They would process the samples with chemicals to isolate the pollen grains. Then, under a high-powered microscope, they would identify and count the different types of pollen in each sample. The story the pollen told was dramatic. In the layers of the core that dated to before the Norse arrival, the pollen was dominated by native Greenlandic plants birch, willow, and sedges. Then, at the layer corresponding to the late 10th century, the pollen profile changed abruptly. The tree pollen, birch, and willow dropped sharply. In its place, the pollen from grasses and weeds like sorrel and buttercup exploded. These were plants that thrive in open, disturbed ground and pastureland. This was a clear environmental signature of the Norse landnum. The settlers were cutting down the scrubby woodland to create pastures for their sheep, goats, and cattle. The pollen was a direct record of deforestation. The pollen also told the story of their farming. The scientists found pollen from plants that were not native to Greenland, like barley. This was evidence the Norse were trying to grow crops, though the pollen counts were low, suggesting they had limited success. More telling was the presence of pollen from pasture-related plants that are often associated with grazing pressure. As the scientists moved up the core, through the layers representing the 12th, 13th, and 14th centuries, they saw another change. The pollen from grazing-related plants started to decline. Pollen from native plants started to reappear. This suggested that farms were being abandoned. The landscape was slowly healing itself. The decline was not a sudden event. It was a slow, creeping process that took place over several generations. The pollen didn't provide a single, simple answer to the mystery of the disappearance. But it ruled out a sudden catastrophe. It showed a long, slow decline. It pointed to a society that was struggling to sustain its way of life in a marginal environment. Their farming practices were changing the landscape, and a cooling climate, a fact confirmed by other scientific methods, was making their lives harder. The story of the lost colony wasn't written in sagas or runes. It was written in microscopic grains of dust, a silent witness to a society's long, slow end. Number 5. We looked inside a king's runestone with medical technology. The Jelling stones stand in a churchyard in the town of Jelling, Denmark. They are two of the most important historical documents from the Viking Age. The smaller stone was erected by King Gorm the Old in the mid-10th century. The larger one was raised by his son Harold Bluetooth around the year 965. Harald's stone is famous for its inscription, where he boasts that he won all of Denmark and Norway and made the Danes Christian. It is sometimes called Denmark's birth certificate. For over 1,000 years, this massive three-sided granite stone has stood exposed to the Danish weather. In the late 20th century, conservators became worried. They could see small cracks forming on the surface. They feared that water was getting inside the stone, freezing in the winter, and slowly breaking it apart from within. But how could they know for sure? You can't just cut open a national treasure. In the year 2000, a team of scientists and engineers came up with a radical solution. They decided to give the Jelling stone a medical checkup. They would perform a CT scan on it, just like a doctor would use on a patient to look for internal injuries. The problem was one of scale. A medical CT scanner is designed for a human body. The Jelling stone is nearly 2.5 meters tall and weighs around 10 tons. You couldn't take the stone to the hospital, so they had to bring the hospital to the stone. They brought in a massive mobile industrial CT scanner, typically used for inspecting rocket motors or large machine parts. The machine was so big it had to be transported on a huge truck. They built a special climate-controlled building around the Jelling stone to protect it during the procedure. Then, the scanner on its heavy gantry was carefully moved into place. A CT scanner or computed tomography scanner works by taking a series of X-ray images from different angles around an object. A computer then combines all these two-dimensional slices to create a detailed three-dimensional image of the object's interior. For several days, the giant machine slowly circled the ancient stone, bombarding it with X-rays. The data was collected and processed. For the first time, human beings could see inside Harold Bluetooth's monument. The results were a relief. The 3D model created by the scan showed that the cracks on the surface were mostly superficial. They did not penetrate deep into the stone. The internal structure was sound. The risk of the stone splitting apart was low. The scan gave the conservators the crucial information they needed to plan the best way to protect the stone for the future. They ended up designing a beautiful and protective glass enclosure that now shields the stone from the rain and frost. The CT scan also revealed something new about the stone's creation. The 3D model showed the internal structure of the granite. The carvers who created the intricate designs on the surface had clearly understood the stone's natural grain and weaknesses. They had worked with the stone, not against it. The project was a remarkable meeting of the ancient and the ultra-modern. A 10th century king's proclamation, carved in granite, was examined using 21st century medical imaging technology. The scanner didn't reveal any lost secrets of the Viking kings, but it did provide the knowledge needed to save their legacy for the centuries to come. It was a high-tech conservation effort to protect one of the world's most important low-tech documents. Number 4, we dated an execution with a handful of atoms. In 2009, during the construction of a new road in Dorset, England, workers uncovered a mass grave. It was a pit filled with the skeletons of more than 50 young men. They had all been beheaded. Their heads were stacked in a neat pile to one side. It was a scene of brutal, organized violence. But who were these men? And when did this happen? The initial archaeological evidence pointed to the Viking Age. Several of the skeletons had filed teeth, a practice known among some Viking warriors. One of the bodies had a chemical signature in its bones, suggesting a childhood spent in a cold climate, far north of England, possibly in Scandinavia. It looked like a group of Vikings who had met a grim end. But to be sure, the archaeologists needed a precise date. This is where an advanced form of radiocarbon dating called accelerator mass spectrometry, or AMS, came in. Traditional radiocarbon dating worked by measuring the radioactive decay of carbon-14 atoms in a sample. It required a relatively large sample of organic material, a big chunk of bone or charcoal. AMS dating is thousands of times more sensitive. It doesn't wait for the atoms to decay. It counts the atoms directly. Here's how it works in simple terms. All living things absorb carbon from the atmosphere. A small fraction of that carbon is the radioactive isotope carbon-14. When an organism dies, it stops absorbing carbon, and the carbon-14 it contains begins to decay at a known constant rate. By measuring how much carbon-14 is left in a sample compared to the stable carbon-12, scientists can calculate how long ago the organism died. With AMS dating, a tiny sample of bone is taken. It is chemically treated to extract the carbon. This carbon is then put into a particle accelerator. The accelerator uses powerful magnets and electric fields to separate the different carbon isotopes based on their mass. A detector at the end of the accelerator then counts the individual carbon-14 atoms. Because it is so sensitive, AMS can get a reliable date from a sample as small as a grain of sugar. The team at the Oxford Radiocarbon Accelerator Unit took samples from the bones of the executed men. Because AMS requires such small samples, they could take multiple samples from different skeletons in the pit to make sure they were all from the same event. The results came back. The AMS dates were incredibly consistent. They all clustered in a narrow window of time between 970 and 1025 AD. This placed the executions squarely in the reign of the English king Æthelred the Unready. This was a period of intense conflict between the Anglo-Saxons and Viking raiders. History records a specific event from this period. The Anglo-Saxon Chronicle states that on St. Brice's Day, November 13th, 1002, King Æthelred ordered that all the Danish men in England should be killed. He feared they were plotting to betray him. It was a brutal act of state-sponsored ethnic cleansing. The AMS dates from the Dorset grave fit this event perfectly. While it is impossible to be 100% certain, the scientific evidence strongly suggests that the 50 beheaded men were a group of Viking mercenaries or settlers who were rounded up and executed on the king's orders. The AMS technology gave the archaeologists the precision they needed. It didn't just place the event in the Viking Age. It narrowed it down to a specific historical window of just a few decades, allowing it to be connected to a known historical event. It gave a name and a date to a forgotten atrocity. The counting of a few thousand atoms in a machine allowed us to hear the end of a very brutal story. Number 3A. Computer found the signature of a Viking craftsman. Viking Age art is full of beautiful and complex objects. Brooches, pendants, and sword hilts are often covered in intricate patterns of interlacing animals and abstract designs. For art historians and archaeologists, one of the big challenges is to figure out where and when these objects were made. Can we identify the work of a specific workshop or even a single artist? Traditionally, this has been done by eye. An expert looks at two brooches and says, "The style of the animal's head on this one is very similar to the style on that one. They probably came from the same workshop." It is a process that relies on a scholar's experience and memory, but it is also subjective. In recent years, a new approach has emerged, driven by computational power. Dr. Mark Haughton, an archaeologist at the University of Oxford, wanted to see if a computer could be trained to see these patterns more objectively. The field is known as computational archaeology or archaeoinformatics. His test case was a type of object called an oval brooch. These were worn in pairs by Viking women to fasten the straps of their overdresses. Thousands of them have been found. They are often decorated with a style of art known as Boré style, which was popular in the 10th century. Dr. Haughton took high-resolution 3D scans of hundreds of these Boré-style oval brooches. The 3D models captured the fine details of the carvings far more accurately than a 2D photograph ever could. He then fed these 3D models into a computer. He used a type of algorithm known as a machine learning model. He essentially taught the computer to recognize the key features of the Boré style. The computer learned to identify specific shapes: the curve of a hip, the shape of an eye, the way a ribbon interlaces. It broke down the complex designs into a set of measurable geometric data points. Once the computer was trained, it could do something a human eye struggles with. It could compare hundreds of brooches simultaneously and measure their geometric similarity with mathematical precision. It wasn't looking for a general style, it was comparing thousands of specific data points. The results were fascinating. The computer began to group the brooches into distinct clusters. These clusters were not random. They often grouped brooches that were found in the same geographical region. The algorithm had independently discovered regional artistic styles. For example, it identified a Gotlandic style from the Swedish island of Gotland that was distinct from the style of brooches made in mainland Denmark. Even more excitingly, the computer sometimes identified very small, tight clusters of brooches that were almost identical in their geometric signature. These were objects so similar that they were likely made in the same workshop, or perhaps even by the same craftsman, using the same set of molds or patterns. The technology is not replacing the expert, it is giving the expert a new tool. The computer can sift through vast amounts of visual data and find subtle patterns that the human brain might miss. It provides objective mathematical evidence to support or challenge the art historian's interpretation. This approach is changing how we study ancient art. It's moving from subjective descriptions to objective data. The computer is not telling us what the art means, but it is helping us understand how it was made and distributed. It is revealing the hidden social networks of Viking Age artisans, connecting a brooch found in Iceland to one found in Russia because a machine was able to recognize the unique mathematical fingerprint of the person who made them. Number 2, we are searching for sunken longships with robotic submarines. The Vikings were a maritime people. Their ships were the key to their world for trade, for exploration, and for raiding. Thousands of these ships must have been lost over the centuries, sunk in storms, wrecked on coastlines, or lost in battles. But finding a Viking shipwreck is incredibly rare. The deep, cold, dark waters of the Norwegian fjords and the Baltic Sea are very good at hiding their secrets. For centuries, the only way to find a shipwreck was by accident, as a fisherman snagging his nets or a diver stumbling across some old timbers. But now, archaeologists are actively hunting for them, using robots to explore the depths where humans can't easily go. The key technologies are sonar and remotely operated vehicles, or ROVs. The search often begins with sonar. A research vessel will use a side-scan sonar, a device towed behind the boat that sends out fans of acoustic energy. It's like shouting into the dark and listening for the echo. The sonar creates a detailed acoustic image of the seabed. A shipwreck will show up as a clear anomaly, a shape that doesn't belong to the natural geology of the seafloor. In 2018, a team from the Norwegian University of Science and Technology NITNU was surveying the waters off the coast of Avaldsnes, Norway. This was the site of a royal manor for Harald Fairhair, the first king of Norway. It was a major center of power in the Viking Age. The team, led by archaeologist Arne Emil Christensen, knew it was a promising place to look. Their sonar picked up something interesting. It was a long, thin shape on the seabed in about 15 meters of water. It looked like it could be a ship, but a sonar image is just a shadow. To know what's really there, you need to go and look. This is where the ROV comes in. An ROV is a small, unmanned submarine connected to the surface ship by a long cable, or tether. The cable provides power and sends data. The ROV is equipped with high-definition cameras, powerful lights, and often manipulator arms. The pilot sits safely on the ship, flying the robot with a set of joysticks, watching the view from the robot's cameras on a screen. The NTNU team deployed their ROV to investigate the sonar target. The pilot on the ship carefully flew the robot down through the murky water. The robot's lights cut through the darkness. On the screen, the seabed came into view. The pilot navigated the ROV towards the anomaly. And then it appeared out of the gloom. It was wood, old dark planks of wood held together with iron rivets. It was the remains of a clinker-built vessel, the classic Viking style of shipbuilding. The ROV spent hours carefully documenting the site. It flew slowly along the length of the wreck, its cameras recording every detail. The archaeologists could see the shape of the hull. They could see how the planks overlapped. They could see how well it was preserved. The ROV allowed them to make a detailed, non-intrusive survey of the site without sending a single diver down into the cold, dark water. This technology is opening up a whole new frontier for Viking archaeology. ROVs can go deeper, stay down longer, and operate in more dangerous conditions than human divers. They are being used to systematically survey the major waterways and harbors of the Viking world. Somewhere in the deep dark mud of a Norwegian fjord, there are almost certainly more ships waiting to be found. The robots are the scouts, the electronic eyes, searching the darkness for the lost fleets of the Viking Age. Number 1, we know what was in their pots because of lingering fats. What did the Vikings actually eat? The sagas talk about feasts of roasted meat and ale. Archaeologists find animal bones at settlement sites, which tells us they ate beef, pork, and mutton. They find carbonized grains, which tells us they grew barley and oats. But what about the everyday meals? What was bubbling away in the stew pot over the fire in a longhouse on a cold Tuesday night? For a long time, this was almost impossible to know. Food decays. But a new scientific technique is allowing archaeologists to find the ghosts of meals cooked over 1,000 years ago. The science is called lipid residue analysis. Lipids are fats, oils, and waxes. They are a fundamental part of all living things. And they are surprisingly durable. When you cook food in an unglazed ceramic pot, some of the fats from the food soak into the porous clay of the pot wall. Even after the pot is broken and has been lying in the ground for a millennium, tiny traces of these fats can remain trapped in the ceramic fabric. Dr. Martin Rundqvist, an archaeologist from Sweden, was part of a team that excavated a Viking Age trading site on the island of Gotland. They found many fragments of pottery. He wanted to know what these pots had been used for, so he sent some of the shards to biochemists at the University of Bristol in the UK. The process is like a form of chemical archaeology. In the lab, the scientists first grind a small piece of the potsherd into a powder. They then use solvents to extract any preserved lipid molecules from the powder. This extract is then run through a machine called a gas chromatograph mass spectrometer. This machine separates the different molecules in the sample and identifies them based on their unique chemical structure. The results from the Gotland pottery were a window into the Viking kitchen. The analysis identified the chemical signatures for fats from ruminant animals like sheep and cattle. This was no surprise. They also found fats from pigs, but then they found something else. They found lipids from marine animals. The Vikings were cooking fish or seals in their pots. This might seem obvious for people living on an island, but it was important proof. The animal bones found at many Viking sites are often dominated by farm animals. The lipid analysis showed that food from the sea was a much more important part of their diet than the bone evidence alone suggested. It gave a more balanced picture of their diet, but the most exciting discoveries come when the analysis finds something unexpected. At another site, archaeologists were analyzing residues from small ceramic lamps. They found the chemical signature for blubber from seals and whales. This told them exactly what the Vikings were using for fuel in their lamps. At a Viking trading town in Sweden called Birka, lipid analysis on pottery fragments turned up something truly exotic: castoreum. This is a substance produced by beavers. It was highly valued in the ancient and medieval world as a medicine and as an ingredient in perfume. The discovery of beaver fat in a pot at Birka wasn't about what someone had for dinner. It was evidence of international trade in luxury goods. The Vikings were processing and trading this valuable commodity. This technology is changing our understanding of the Viking economy and diet. It's giving us direct evidence, molecule by molecule, of what was being cooked, processed, and traded. A small, plain piece of a broken pot can now tell a story that was once lost forever. It can tell us about a simple family meal or a link in a global trade network, all because of the lingering echo of a long-vanished fat.